Welcome back to the deep dive. I was staring at the stack of research you sent over for this week.
The pile, you mean?
The pile, yes, and I had this weird moment of nostalgia for, of all things, high school physics class.
Physics. That feels like a bit of a detour from where we're supposed to be heading today.
No, stay with me here. In physics, the history feels so clean. You start with Newton.
Right. Apples falling, classical mechanics.
Everything is orderly. Then Einstein walks in, drops the theory of relativity, and basically says, "Nice try, Isaac, but this is how the universe actually works." The old theory gets replaced by the better theory. It's a straight line.
I see where you're going. You're talking about a paradigm shift. One model creates a crisis, the new model solves it, and, well, everyone moves on.
Exactly. But then I look at today's topic, linguistics, specifically the history of how we teach computers to understand language. And it is not a straight line. It's a messy, chaotic battle royale. It's not one Einstein replacing another. It's like different tribes setting up camp on the same mountain and just refusing to talk to each other.
That is a painfully accurate description.
Language is just, well, it's significantly more variable than gravity. You can predict where Mars will be in 1,000 years with extreme precision.
Right.
But you cannot predict with 100% certainty how a teenager in Los Angeles will use the word literally next week.
Or skibidi.
Please don't start. But yes, because language is this biological and social chaos, we don't get that clean Einstein moment. Instead, we have these massive coexisting evolutionary paradigms.
And that is our mission today. We are going to unpack the two heavyweights of this history. The two main ways scientists have tried to turn human speech into code. On one side, we have the constituency approach, the American tradition, the Chomsky tradition.
Which is all about nesting, putting words into boxes and then putting those boxes into bigger boxes.
And in the other corner, we have the dependency approach, specifically the meaning text theory, which is completely different. That's about networks. It views language as a web of links connecting individual words, almost like a constellation.
It is the battle of the boxes versus the arrows.
Yeah.
But before we get to the computers and the algorithms, we have to rewind a bit.
Right.
Because this didn't start with code. It started with people trying to prove that linguistics was a real science.
Right. If you go back to the early 20th century, you hit Ferdinand de Saussure. And he's the one who really said, language isn't just a pile of words, it is a structure. That gave birth to structuralism.
Okay.
But the real shift, especially for our story, happens when the Americans get involved in the 1920s and 30s.
This is the Leonard Bloomfield era.
It is, and you have to understand the vibe of American science at the time. They were obsessed with objectivity.
Right.
If you couldn't see it, weigh it, or measure it, it wasn't science. They didn't want to talk about thoughts or meanings, because you can't see a thought.
So what can you see?
You can see word order. You can see that the dog bit the man is different from the man bit the dog.
Those are observable facts.
Exactly. So the American structuralists started analyzing language strictly by how words are arranged.
Which sets the stage perfectly for the 1950s. The computers turn on and enter the tightening of the field. Noam Chomsky.
It's hard to overstate how much Chomsky changed the game. Before him, linguistics was a lot of, cataloging. Chomsky came in and said, no, language is mathematics. He introduced generative grammar.
Okay, generative grammar. I see this term everywhere. The sources link it to context-free grammars or CFGs. Help me visualize this. When I look at the diagrams in the notes, it just looks like a family tree.
It's very similar to a family tree, or maybe a better way to put it, it's like a set of nesting dolls.
Oh, okay, I like that.
The core idea is constituency. You start with the biggest doll, the sentence. We label that S.
Okay, I have my S doll.
Exactly. Now, you crack that open. Inside, you don't find words yet. You find two smaller dolls, a noun phrase, or NP, and a verb phrase, VP.
Okay, so a sentence isn't a string of words. It's a noun phrase plus a verb phrase.
Correct. Now you take the noun phrase doll, you crack that open, and maybe you find a determinate like the word the and a noun like student. You keep breaking these categories down until you finally hit the actual words.
So let's use the example from the reading, this Spanish sentence. La estudiante canta una canción. The student sings a song.
Right. In the Chomsky model, you don't just read that left to right, you build it top down. S becomes NP and VP. The NP becomes la en estudiante. The VP breaks down into the verb canta and another noun phrase, una canción.
It's hierarchical. Everything belongs to a category, which belongs to a bigger category.
And that was the appeal. It looked like computer code. You could write simple rules. Rule 1, S becomes NP plus VP. Rule 2, NP becomes a determiner plus a noun.
Yeah.
If you program those rules into a computer, it can generate sentences.
But, and there's a huge but here, the source points out that while this looked elegant on a chalkboard, it was actually kind of a disaster for meaning.
It was, because the rules were too simple. They were context-free. The rule just says, put a noun here. It doesn't care which noun.
So if I have a rule that says noun phrase, verb phrase, and I just plug in random words.
You might get la estudiante canta, the student sings. That's great. But the same rule might give you canción del María.
Song sees the Mary.
Grammatically, according to the boxes, it's perfect. You have a noun, a verb, and a noun. But semantically,
It's complete gibberish.
complete gibberish. Songs don't have eyes. They can't see Mary.
This is the garbage in, garbage out problem.
Yeah.
The system knows where the blocks go, but it doesn't know what the blocks mean.
Precisely. The symbol S, or NP, is just an abstract label. It has no concept of aliveness or ability to see. But there was an even bigger mechanical problem with the nesting dolls.
Which was?
They can't handle movement.
Movement. You mean like words changing places in a sentence?
Exactly. Think about a question. In English, if I say, John sees Mary, that fits the boxes perfectly. Noun, verb, noun.
Right.
But if I want to turn that into a question, what do I say?
Does John see Mary?
Right. Does John see Mary? Look at what happened. We added a word, does, and we stuck it at the very front.
Okay.
But in the deep structure, does is connected to the verb see. They belong together. By moving it to the front, you've ripped it out of its verb phrase box and stuck it somewhere else.
You've broken the nesting doll.
The nesting doll is shattered. The neat hierarchy failed because words in human language love to move around.
So Chomsky had to patch the code,
He did. He introduced transformational grammars.
which sounds like a simplified cartoon robot. Transformers. More than meets the eye.
It was a bit like that.
Ah.
He basically added a second layer of rules. You start with the deep structure, the nice, neat nesting dolls.
Yeah.
Then you run a transformation program, literally a set of instructions that says, take the auxiliary verb, move it to the front, and flip the subject.
So it's a patch. It's like, okay, the model doesn't work naturally, so let's write a script to force the words into the right order.
It worked in the sense that it could describe English. But the source mentions that this is where the theory lost its mathematical elegance. It became messy. You had to write a specific transformation rule for every single weird quirk in the language.
So that was the 50s and 60s. But eventually people got tired of the spaghetti code.
They did. They wanted to fix the boxes without all the movement rules. And this brings us to the next phase, the constraint-based approach.
Right. By the 80s, linguists were thinking, maybe the problem is that our boxes are too dumb. A noun phrase is too vague. We need more data attached to these boxes.
And this is where we start talking about valencies.
I remember this from chemistry. Atoms have valencies open slots where they can bond with other atoms.
It is the exact same concept. They realize that verbs act like chemical elements. They have specific requirements. Take the Spanish verb dar, to give. You can't just use it in isolation.
Right.
I give.
You give what? To whom?
The sentence feels broken. The verb dar has a valency of 3. It demands a subject, the giver, a direct object, the gift, and an indirect object, the receiver.
So instead of a generic verb box, we now have a verb that demands 3 friends box.
Exactly. And this led to the idea of constraints and features. Instead of moving words around with transformations, we just write complex equations to make sure the words agree.
The source gets pretty technical here with head-driven phrase structure grammar, HPSG. But the coolest part, I thought, was this concept of unification.
Unification is a fascinating algorithm. It's basically a mathematical compatibility test.
Walk me through this, because the example in the text used las estudiantes, and I want to make sure I actually get it.
Okay. So in Spanish, articles and nouns have to match gender and number. Las is the, but specifically for feminine plural things.
Got it. Las equals feminine plus plural.
Now look at the noun estudiantes, students. In Spanish, ending in E is tricky. Estudiante can be a male student or a female student. The word itself doesn't tell you.
It's neutral.
In linguistics, we say it is underspecified. It has a plural feature, but the gender feature is blank. It's a variable waiting to be filled.
Okay, so I have one puzzle piece that is clearly pink, las, and another puzzle piece that is sort of gray, estudiantes.
When the computer tries to combine them into a noun phrase, it runs unification. It overlays the features. It says, okay, plural matches plural. Good. Now, las says gender is feminine. Estudiantes says gender is whatever you say it is.
So the noun just accepts the gender from the article?
Yes. The information unifies. The blank slot gets filled. The resulting phrase los estudiantes is now locked in as feminine plural.
That is surprisingly clever.
Yeah.
It's like the words are negotiating with each other to figure out what they mean.
That's a great way to put it. And HPSG used this to handle massive complexity without needing those clumsy movement rules from the Chomsky era.
We're still talking about boxes. We're still grouping things into phrases. Meanwhile, on the other side of the Atlantic, something totally different was happening.
Yes. While the Americans were polishing their phrase structures, the Europeans and Russians were developing a completely different paradigm. This is the meaning text theory, or MTT.
And the main characters here are Igor Melchik and his colleagues.
Melchik is a giant in the field, and he took a different philosophical stance. He didn't care as much about generating sentences from a blank slate. He viewed language as a transformer.
Transformer.
You input meaning, you get out text. You input text, you get out meaning.
And the visuals are completely different. No more nesting dolls.
No dolls, no boxes. They use dependency trees. Picture a sentence written out. Instead of drawing brackets around groups of words, you draw an arrow, a link from one word to another.
A direct connection.
Direct. In the small boy, you'd have an arrow from boy to the, and an arrow from boy to small. The boy is the governor. The others are dependents.
Why does this matter? Is it just a different way of drawing the same thing?
It matters immensely for one big reason: word order. Remember how Chomsky's boxes broke when we moved booze to the front of the sentence?
Yeah, the box shattered.
In a dependency tree, that doesn't happen. The link between does and see is just a line. If I move does to the other side of the page, the line just gets longer. It doesn't break.
Oh, I see. It's like they're connected by a rubber band. You can stretch it, twist it, move the words anywhere, but the connection remains.
Exactly. And this is why dependency grammar became so popular for languages like Russian or Latin or Spanish, where you can put words in almost any order you want.
Right. The source mentioned this. In Spanish, you can say, Juan ama a Maria, John loves Mary, or a Maria la ama Juan.
Where the subject Juan is at the end, the object Maria is at the front. A constituency tree would be a tangled mess trying to draw boxes around that.
But a dependency tree.
A dependency tree just draws an arrow from Ama to Juan and Ama to Maria. It doesn't care where they sit on the page.
That feels so much more robust for real-world speech.
It is. And to manage this, Melchik's team developed something called government patterns.
This sounded incredibly bureaucratic when I read it. Government pattern. It sounds like something I need to file with the IRS.
It's actually just a very, very detailed script for every verb. Remember valencies.
The donator, donation, receiver thing.
MTT takes that to the extreme. For every single verb in the dictionary, they map out exactly what creates the meaning. And they make a crucial distinction between actants and circumstance.
I love these terms. Break them down for us.
An actant is a main character. The verb implies them. If I say to give, there has to be a giver and a receiver. Even if I don't say who they are, the concepts are built into the verb.
Okay. And a circumstant.
That's the scenery, the context, in the park, yesterday, quickly. These are optional. You can add in the park to I gave, I ran, I slept. It doesn't change the nature of the verb itself.
So actants are the cast list, circumstants are the set dressing.
Perfect. And this distinction allowed computers to finally understand the scene of a sentence rather than just the grammar. But the most sci-fi part of MTT, and the part that I think is most relevant to AI today, is the deep syntactic level.
Yeah, this part tripped me up a bit. The theory says you can transform sentences deep down in the code.
It says that words are just surface decorations for meaning. And sometimes totally different words can act out the exact same meaning.
Give me an example.
Okay, compare these two sentences. John let me help and John helped me.
Lent help versus helped, they mean the same thing.
But structurally, they are totally different. One has a noun help, the other has a verb helped. A computer looking at the surface thinks they're different events. But MTT says, at the deep syntactic level, we can run a transformation rule that equates them.
So the computer knows they're synonyms, not just from a dictionary, but from the structure.
Right. And sometimes the theory goes even further. It will restore words that aren't even there.
Invisible words.
Logical placeholders. The source gives an example of a phrase like, his son Juan.
Okay.
Structurally, Juan is the name of the son, but there's no word connecting them like named. MTT suggests that at the deep level, the computer inserts a node called name, so the link goes son, arrow to name, arrow to Juan.
It's forcing the logic to be explicit. It's saying, hey, human, you skipped a step here, so I'm going to write it in so the math works.
Exactly. It's prioritizing the logic of the meaning over the sound of the sentence.
So we have these two massive tribes, The constituency folks, Chomsky, HPSG, building their nested boxes, focusing on hierarchy, and the dependency folks, Melchuk, MTT, drawing their webs, focusing on the links between words.
And for decades, they barely spoke to each other. They published in different journals, went to different conferences.
But here is the thing that blew my mind in the reading. It's not just that they disagree on the solution. They disagree on the definitions of the words they use.
This is the Tower of Babel problem in linguistics.
We talked about deep structure and transformations earlier.
Right. If you ask a Chomskyan, what is a transformation, they'll say, it's a movement rule. It moves does to the front of the sentence.
But if you ask a Melchuk fan,
They'll say, no, a transformation is replacing lent help with helped to preserve meaning.
they're using the exact same technical terms to describe completely different operations.
And deep structure. For Chomsky, deep structure is just the basic word order before things get moved around. For Melchuk, deep structure is a semantic abstraction where invisible nodes like name exist.
So imagine being a young student trying to learn this field. You open one textbook, deep structure means X. You open another, it means Y.
It creates a tremendous amount of noise. It makes you wonder, how much of our struggle to build true AI was caused not by a lack of computing power, but by the fact that our architects couldn't even agree on the blueprints?
That is a haunting thought. We spent 50 years arguing about the shape of the map instead of driving the car.
In a way, yes. But I think the modern takeaway is that both were right.
How so?
Look at how we use language. Sometimes we do think in blocks. The President of the United States is a block. We move it around as one chunk. That's constituency.
But sometimes we just link ideas. I pizza one.
Exactly. The links matter. Modern natural language processing, the stuff driving ChatGPT and others, it effectively stole the best parts of both. It uses the attention mechanism, which is basically a massive superpowered version of dependency links.
So the arrow's kind of won.
In the neural network world, the arrows are definitely doing the heavy lifting, but the boxes gave us the structure to understand what we were looking at in the first place.
So here's my challenge to you listening right now. The next time you are talking, maybe you're explaining something complicated to a coworker or just ordering coffee, try to visualize your own speech.
Are you building nesting dolls? Are you grouping a large soy latte with vanilla as one big unbreakable block?
Or are you spinning a web? Are you just throwing out key concepts, latte, soy, vanilla, and relying on the invisible rubber bands of logic to pull them together for the listener?
You'll probably find you're doing both, usually at the same time.
And that is the messy, chaotic miracle of language. Thanks for diving in with us.
A pleasure as always.
We'll see you on the next one.